All right, Jeff. So where were we? Sorry about that. So internet here sucks. Software sucks. Just mad about everything. Maybe he's sleepwalking. Yeah, and then my iPad was dead. I couldn't even check anything to see what was going on. I can combine them before uploading. Okay, good. So we're recording a second little thing here, and we'll just combine them. So we were working on this problem. Sun, Mercury, Earth in that order. Yeah. So let's just worry about this setup. So we're gonna look at Mercury going to about here, and it'll be traveling in the same direction as the Earth. It's 36 million miles, and it's finishing in 88 days. So I guess if we have a measure of time in years, then in 1 year it's gonna go 88 over 365 radians of angle. Converted to radians, of course. Let's see. So yeah, so obviously their initial distance is just the difference of the two. So let's look at the distance formula. So distance formula is going to tell us that the distance between them is going to be, well, actually, let's just parameterize them both first, right? So Mercury is going to be parameterized as x is, so first we're going to start out, yeah, you wrote it in the chat, right, Jeff? Jake, you really can't just be constantly asking, can you do this problem? Can you do that problem? Like, also a lot of the problems you're giving us, you're not giving us enough information to solve the problems. So that's going to make it less likely to get your problem solved. So we're trying to parameterize 36 times cosine 2 pi t over 88. Yep. Cosine 2 pi t over 88. Yeah, so that if we do a full, wait. Is this for Mercury? Right, when we go 88 days around. Okay, so t is in days here, right? So t is in days. Yeah, so if we go 88 days, then we go full lap around, which is 2 pi, right? So then y is 36, in millions of miles, of course. Over 88. Where t is in days, yep. Then we have the other parameterization for the Earth, and that one will be similar, but it's going to be 93 million miles. And similar, yeah. Cosine 2 pi 365 on the bottom. Let's erase that because I think what I had written there wasn't even correct. Okay, so we got Mercury parameterization, Earth, and we're going to want to know the distance between these two xy points at every given time t. That's going to be the distance, and then the average distance. Of course, we're going to need to know how long this period we're taking the average over. Like you were saying, Jeff, either we need to figure out, how many periods is it going to take, how many years is it going to take for these to both kind of match up back at the same point, which if there's some rational, relationship between these two angles here, I think maybe here there is, then they should meet back up, right? Yeah, as long as the ratio between these two angle is a rational number, I think then we're fine, which here it is. So yeah, I think you would just need to calculate like how many days is it going to take for these to, match back up, which I think it has something to do with the LCM of these two numbers, right? 88 and 365. So what's the least common multiple of 88 and 365? And Earth is 93. Yeah. Look at the difference in angles. You can find out when it's 2 pi. Well, I think it should just be the least common multiple of these two numbers, right? I think it should be that many days. So yeah, I could figure this out, but does someone want to give me what the least common multiple is here? And I'll slow down for the add, but so this should be some number of periods. This should give us the number of periods until they meet back up at the same point, basically. Because if we do one Earth rotation, right, they're not, unless 88 fully divides 365, they're not going to meet back up here after one Earth rotation. Then we'll have to do 2 Earth rotations, or however many Earth rotations we need until these numbers, basically, we need some common multiple of these. Yeah, that's exactly what we need. So we need the least common multiple of these two number of days. Right. So, is that n here, Jeff? I'm not sure if is that the same number. You're saying 32120 divided by 277. But I'm not sure if that's the same thing as this n. Can someone figure out, or can you type this into Wolfram or something? I mean, I don't have the factorizations on the top of my head, so I'm not sure what this LCM is. I could look it up though. 88 times 365. I guess you could do it doesn't need to be the least common multiple, it just needs to be a common multiple. Yeah, you're correct. Alright, fine. Yeah, I guess we could just take the product of the two. That works too, yeah. So it'd be like 1 over 88 times 365. Integral from 0 to 88 times 365. Then it's going to be the distance between these 2 points at any given time. Yeah, times dt. Yeah, so it'll be 93 sine squared of this minus 36 sine squared of that. So basically a difference of 2 sine squareds plus a difference of 2 cosine squareds. So you're going to have cosine squared plus sine squared, I think, minus another one. So yeah, let's try to write it out. So what goes here? Let me leave this up. Saying compute when Mercury's angles is 360 higher than Earth's. Integral control find a closed form. Well, not quite. Yeah. Oh, okay. So it's a little bit different. Oh, sorry. Yeah, you're right. It is 93 sine minus 36 sine squared, right? Yeah. So are we able to integrate it at the end, or is this like something that you just need to approximate? So it's going to be like I'll just put A here. A is equal to this product, okay? So So 88 times 365. Integral from 0 to a of the distance, so 93. Oh, right. Yeah, I said that wrong, my bad. 93 sine 2 pi t over 88, or over 365, minus sine of 2 pi t over 88 squared. The whole thing squared. Plus, 93 minus 36. Times the other sign. Plus, similar. Squared dt. The end. Difference of sign. That's where I ran into trouble. I couldn't find a good closed form for the integral, and then square root of the whole thing. Yeah, I mean, a lot of these integrals aren't going to have a closed form though, so it's possible that, this one. I don't feel so confident that this one has a nice closed form. So you may just need to use like some Riemann approximation for the integral or something like that. I don't know. Yeah, just looking at this one, it doesn't look very good. And if you're saying, like, I would just type it into Wolfram, I mean, just looking at it, it looks pretty bad. I don't think it has a closed form. That's what you got. Oh, an elliptic integral? Yeah, I mean, this is looking like some sort of, I don't know if it's an elliptic integral, but it's, I mean, if you did out the square, yeah. I mean, you basically have like squares of two different signs of different periodic orbits. You get some weird middle term that's like some cross term that also is not constant. They both depend on t, both the cross terms. Yeah. Maybe some double angle formula or something. I don't know. Maybe there's like some sort of sum of angles formula or something in here. Maybe I see, but which I guess would make sense with this problem, right? But even then, I'm not sure what the antiderivative. Well, I don't know. Maybe it's not so bad, but I don't see it just like looking at it real quickly. Oh, elliptic integral. Okay, so Mathematica gave me an answer, but it involved the elliptic e function. Yeah, so this one probably you're not going to be able to get a nice satisfactory answer unless you just approximate it using some numerical solution, and then you'll probably get some nice solution. Obviously, there has to be some average distance that they travel, and we know it's not infinite because they're just going around the sun. They can't get too far away from each other, right? Yeah, so you should be able to approximate it. It shouldn't be too large of a value, I would think. It's got to be somewhere between the minimum and the maximum, right? The minimum is when they're perfectly aligned here, right? And then the maximum would be when they're, oppositely aligned. So the Earth is here and then the Mercury is here. So the average has to be somewhere between these two distances, right? And you know that, so you can estimate it that way, and then you can find a numerical solution probably pretty easily. Jeff says you can simplify it to holding Earth fixed and having Mercury travel in a slower orbit where x is the distance ratio. You're just saying, yeah, have like view it as like, okay, I think I see what you're saying, but I don't know if that, yeah, I mean, you're probably still going to be stuck with some weird integral, right? So probably going to have to take some sort of numerical approximation at some point, or else you're going to end up with that, elliptic e function, whatever that is. There's all these like, what are they like? The solutions to different differential equations, where some of them are like parabolic. I know a lot of them, they don't have like closed form solutions, but they end up giving them like names because they're so common, even though they're like some analytic function that's, not a polynomial. It's some infinite Taylor series usually. Okay, Jeff's satisfied, so that means I'm satisfied for sure. Um, any other questions here? I think I'll wrap it up soon. Sorry about the internet. I'm gonna try to get it fixed. Like it just keeps going out every hour, and I've had them come and fix it, and it keeps happening. So hopefully it just goes out like once per hour, and that's like the worst. But sometimes it keeps going out multiple times, so I don't know. Yeah, error function, the error C function. What's the difference again? I know error function's like the integral of that, the integral from probability theory. But the error C, is that like some shifted version or something? I don't know. All right, guys. If the other Jake is here, I can go over some of those problems as well. Oh, it's midnight. Oh, okay. You're going to sleep. I'm sorry. I didn't know it was so late. I would have done more of your problems earlier, probably. Oh, the complement. Okay. Right, right. So, like, what? 1 minus the error function? Oh, okay. Error C function. Right, right. Okay, so just 1 minus the error function. Okay. The complementary error function. I like it. All right. We had 2 Jakes in the chat. If the other Jake that's still here and not going to sleep wants to go over any other problems, I'm willing to look at some of those. We got at least four more minutes. I can stick around. Oh, I think Jake wrote in the Wednesday possibly. What did he say? Oh, okay. Use A equals P times 1 plus R over N to the NT to solve this one. I think Rex. Oh wait. Solve the equation. Okay. Are there any of these we want to go over? Anybody in chat still here? Let's see. What did I miss here? Okay. Oh, I guess Rex is going to sleep. Is there no sound? There should be sound. Is anybody getting no sound? We had a couple crashes though, so it's possible you need to maybe refresh. All right, if the other Jake isn't here, I think I'll just call it here. I don't see. Oh, Rex is not asleep yet. All right, guys. I appreciate you watching. If anyone was on YouTube watching or you're watching in the future, definitely subscribe and watch out for us going live. Usually I go live Tuesday, Friday at 4 p.m. and sometimes I'll do exercises on Wednesday at 4 and also at research at 5 p.m. on Saturdays currently. All right. I think that's it. I'll just call it here. And Rex, maybe you could try to raid someone. I'm not sure how to do it from here. Or I can try to do it from here, but I'm not sure if it works. So we'll try to raid someone. If it doesn't work on my end, maybe I could try to have Rex do it, but... Bro. Let's try to Echo-Fi, maybe? Let me see if I can... Echo-Fi. Okay, well, let me send the text, but I'm not sure if it actually...